How can the definition derivative look so complicated and yet the power rule look and feel so simple? Well, this is climb time. In today's video, we're going to look at where the power rule comes from and how it's related to the definition derivative. First of all, if you're not familiar with the power rule, it looks like this. If you have some function that is x raised to some power, we just take the power, move it to the front, and subtract 1 from the power. That's how you find the derivative using the power rule. If you want to look at a quick example, let's say we have y is equal to x cubed. So dy over dx, which is the derivative, is just going to be take 3, move it to the front, and subtract 1 from the power. That's it. The derivative is 3x squared. So that looks and feels very simple. It is one of the most used rules when you find the derivative because every polynomial usually has a power of some sort other than 0. So we use it all the time. It's very easy, and yet it feels very, very removed from the definition derivative. So how is it related to the definition derivative? So we're going to look at that today. But first, let's apply the definition derivative to x to the n. So let's say our function is x to the n. Let's apply the definition derivative. By the way, if you're not familiar with the definition derivative, check out an earlier video I have on where the derivative comes from and why this is the definition. I'll just say real quickly that the derivative is the slope of the tangent line. And so here you see change in y values. H is actually change in x values. So we have change in y over change in x. We have slope here. And by making the h approaching 0, by taking the limit as h approaches 0, what's happening is you have 2 points that are coming increasingly close together to become 1 point. So this makes it tangent, this makes it slope. So it is the slope of the tangent line. All right, so let's apply this now to our current function, which is going to be x to the n. So if we apply this definition to x to the n, we get this. Get the limit as h approaches 0. And we replace x with x plus h to get f of x plus h, and I get x plus h to the n minus, and then f of x is equal to x to the n all over h. And that is us applying the definition of derivative to our current function, which is x to the n. Now, all of this is hinged on something called the binomial theorem. So I have the binomial theorem written down here, and I have put some boxes in here because I want to talk about those in a second. But basically, if you have a binomial, and a binomial is 2 terms, that's where binomial comes from, 2 terms added together, raised to some power, some integer power, n, it'll always come out to this form. So we have some coefficient times a to the n, plus some coefficient times a to the n minus 1 times b, plus some coefficient times a to the n minus 2 times b squared, plus dot, 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 plus some coefficient times a times b to the n minus 1, plus some coefficient times b to the n. Notice there's a pattern here, and this pattern can easily be found by taking a plus b to the 1 and seeing what that comes out to be. A plus b squared, multiplied together, see what that comes out to be. A plus b cubed, multiply that out, see what that comes out to be, and you'll see there's a pattern. And the pattern comes out to be something every single time. This is the general rule for that pattern. And what happens is you'll always get a raised to the n is going to come out of that, and b raised to n is going to come out of that. And then every other combination of powers between a and b comes out of that. So we have a with 1 less power and b to the 1. We have a with the power 2 less than the power, and b squared, and we get the same thing for b. And if you add up the powers, you'll see that every single time the powers come out to be n. So in this case, the power is n because a is raised to n. In this case, you have n minus 1 plus 1. Well, that comes out to be n. So the sum of the powers is always n. Some of the powers is n here, 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 and finally some of the powers is n here. So there's the middle terms. We don't know the number of middle terms because we don't know what n is, but we will have more terms the bigger n is. But this is called the binomial theorem. Our purpose here is not to prove this or to justify it, but we can say this, that if you just multiplied out a plus b to different powers of n, you would see it follow this pattern pretty quickly. Now, you'll notice I did not fill in the boxes. So the boxes also follow a pattern, and the boxes are the coefficients that go in front of each one of these terms. So what goes in those boxes, there's different ways to answer that question, but the way I'm going to answer that question is I'm going to say it's from Pascal's triangle. So Pascal's triangle looks like this. We have a 1, and then we have 1, 1, and then we have 1, 2, 1, and then we have 1, 3, 3, 1. We have 1, 4, 6, 4, 1, and we have 1, 5, 10, 10, 5, 1. This is called Pascal's triangle, where I'm getting those numbers from, and I might have got off the screen a little bit there, but where I'm getting the numbers from is if you take these two, 1 plus 1 is 2, you get that number. You get these two, 1 plus 2 is 3, you get that number. 2 plus 1, 3, you get that number. 1 plus 2 is 3. I guess I already said that. So it's 1s along the sides, but if you add up two numbers, it gives you the number directly below. So 3 plus 3 is 6, 6 plus 4 is 10, 4 plus 6 is 10, 1 plus 4 is 5, and so forth. So that's called Pascal's triangle. Turns out that Pascal's triangle are the coefficients in front of these terms. And again, you would see that if you multiplied out a number of binomials, starting with a plus p raised to the 1, and then a plus p raised to 2, a plus p raised to the 3rd, and so forth. Now, even better, we can start with 0. So up here at the top, this would be n equals 0. So if you had a plus b raised to the 0, that means the whole thing just becomes 1. And so that's why you have just one coefficient 1, because anything raised to 0 is just 1. And then this one would be n equals 1, because if a plus b is raised to 1, all you'd have is a plus b. So your two coefficients would be 1 and 1. And then if you had n equals 2, so a plus b squared, that means you have a plus b times a plus b. And some people are able to multiply this out in their head, but if you have a plus b squared, it's going to be a squared plus 2ab plus b squared. A squared plus 2ab plus b squared. And so it follows that these are the coefficients of the binomial when it's expanded. And if n is equal to 3, it'd be this one, and so forth. So it just keeps following as it goes along. Here's n equals 4, and n equals 5. You can see how that works. Now, what I want to point out here, and I think this is important, is that there's always 1s along the left side, which means the coefficient in front of a to the n will always be 1. And there's always 1s along the right side, so that means the coefficient in front of b to the n will also be 1 as well. So we have a 1 here, we have a 1 here, and there's also something else we can track, and that is the very second term, depending if you want to call this the first term or the second term, but if we call this the second term will always be n. So in this row, n equals 1, that's n. N equals 2, second term is 2. N equals 3, second term is 3. N equals 4, second term is 4. N equals 5, second term is 5. So that means our second term will always be n. So I can write that in. Turns out that the second to last term is also n. So if you look down this way, you can see the second to last term is also n. And so we can write that in as well. So there's some terms we know right off the get-go. The terms in the middle will change depending on, I know the next one. Well, I don't. So the terms in the middle will change depending on the size of n. But what I do know is that this is 1 and this is n. There's a formula for the terms in the middle, but that's not of concern to us. All right, so I think we are now ready to see how this works out. So it's all hinged on the binomial theorem. So if you know the binomial theorem, or if you can accept it, then you can see why the derivative of xn is n times xn minus 1, because it has to do with all the terms you get when you multiply out the binomial theorem. So let's do that. Let's multiply out all these terms, and let's see what happens. So f prime of x is equal to the limit as h approaches 0 of, now we're going to multiply out all these terms, x plus h to the n. So I'm going to use the binomial theorem. And so in this case, my a is x, and my b is h. I'll put it in parentheses so you can recognize that that's this first term here. So I get 1 times x to the n. All right, I get 1 times x to the n. So that's first, I'll just say x to the n. And then the next one is going to be n times x to the n minus 1 times my b, and my b in this case is h. And then plus, don't know the coefficient, I'll draw a box here. I know that now my x is going down 2 in power. And I know my h is going up in power. And I'm going to say plus dot, 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 plus. And now I have n again. And now I have x raised to the power of 1. And now I have h to the n minus 1. And then finally, I have plus h to the n. Okay, and what that represents, this big, long, multiplied out, expanded version of x plus h to the n, it represents the first part in the definition of derivative. So the first part is x plus h to the n, and it's expanded out using the binomial theorem. And so then minus, I still have x to the n, and then all over h. All over h. Okay, and so here's where the magic happens, is we have a lot of cancellation, and this is what I want you to see, is we can see that we have x to the n here, and we have x to the n here. So the x to the n term disappears because of that. All right, so the x n's go away that way. And then we have an h here, and so therefore every term that has an h will lose one of their h's, because we can basically divide out an h and then cancel it with the denominator. So every place you see an h will lose one of its h's. So this one only has one h, so it'll lose it. This has two h's, so it'll lose it and become a power of 1. I'll replace that with a 1. And then this one will lose it, and they'll have 1 less power. And then this one will still have, so this will have 1 less power. So I'm going to cancel that out and say it's now n minus 1, and now it's going to become n minus 2. And then this is going to become n minus 1. But the point is, they will still have h's as long as n is bigger than 2. They'll still have h's. And that's what's going to happen if I cancel out that h. All right, now the next step is we've got to plug in 0 in for h, because its limit as h approaches 0. And what happens is every term that still has an h in it will now go away. So every term that still has an h in it will go away. So that would be this term. That would be every term in the middle. It'd be this term and this term. And so then we're left with, once I plug in h, plug in 0 for h, we're left with exactly what we were looking for. So the derivative comes out to be n times x to the n minus 1. Okay, so where this comes from, so this is the power rule. So where this comes from is when you expand out x plus h to the n using the binomial theorem, it turns out that the very first term cancels with the x to the n. Those cancel out. And then every other term has at least one h in it. And the second term has exactly one h in it. So the second term is exactly one h in it, and so that one cancels the denominator. So once because it has exactly one h in it, that h goes away, and then every other term has at least two h's in it. And so every other term after that has at least two h's in it. And so then once we plug in 0 for h, all the other terms go away. So the only term that is left over is the second term. And that's because it had only one h. And because it had only one h, it cancels with the denominator from that h there. And therefore, there are no more h's left over for 0 to get plugged into it. And so that's the only term that remains from the binomial theorem. And there is your power rule. It's the only term that remains after we simplify. So anyway, that is the power rule. And that is how it's related to the definition of derivative.